Welcome to section 5.3. We're talking about logarithmic functions, day 3. So the big thing to take away from today is that y equals log base b of x is equivalent to x equaling b to the y. They look different, yes, but the main takeaway is that the log is the exponent. Okay, so we'll convert. Here you see y, and then it goes into the exponent. You'll see the base in the first equation becomes the base in the second equation. And x is what's called the argument, and we'll talk through all of that. So the first thing is, let's convert the equation that's right now, example 1, in exponent form, into logarithmic form. So I'm going to take 2, which is my base, and I'm going to put it into the base of my log. So 2 goes to 2. The 8 is equal to x, so that goes right here. And then it's going to equal the y value, which is 3. So however you want to do this, make sure that x gets put into the x position, base put into the base position, and then that log gets put into that exponent. Same thing for this next one. Our base is 10. So we have log base 10 raised to the negative first power. That means it's going to equal negative 1. And x, that argument, is 1/10, is what is inside the log. This is log base 10, you can even put parentheses if you want, of 1/10 equals negative 1. Now let's go the opposite direction. Let's take it from log and put it into exponent. Well, 5 is the base, so make 5 the base. It's going to equal the argument, and the power is 0. And we should know this. Anything to the 0 power is 1, so that's equivalent. Example 4. Take your base, make it the base of your problem. It's going to be raised to negative 2, and that's going to equal the argument. And this we know is true. 3 to the negative half. You can't leave negative exponents. You'll put that on the bottom, and then it would be 1 over 3 squared, which is 9. So again, converting, be comfortable with it, because you might be given it in log form and you want to put in exponential. You might have stuff like which one's larger. So you'll have to critically think in log form, and you kind of get stuck. So, what do I do? Well, we're just familiar now with bringing logs into exponential form, so why don't we do that? 2, and actually we don't know that power, equals 9, so I'm going to put maybe like a little bubble, because we don't know, it doesn't equal anything. Compare it to 6 raised to a power, equaling 30. So I'm trying to, in a weird way, compare the two clouds. They're going to be different. I'm trying to figure out which one's larger. Well, let's think about it. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. So regardless of what this power is, I know it's going to be greater than 3. Because 2 cubed is 8, and we need to be above 8. We're trying to get to 9. Same thing with 6 raised to the first power is 6. 6 raised to the second power is already 36. So in order to get to 30, I actually need to be less than 2. And when I'm talking about it, I'm talking about these exponents. So which one's larger? Obviously, when something's greater than 3. So that is the log base 2 of 9. Okay, you kind of have to think about what powers gets you close to the argument, and then compare those. Example 6, evaluate a logarithmic expression. Okay, now when it's an expression and it's in logs, our first step is let's change it into exponent. That means you'll have 4 raised to a power, we don't know what that is going to equal my argument of 32. That's just log to exponential. Well, realize we have this special rule that if you have the same base that are equal, so maybe equal same base, then you're going to have equal exponents. So let's see, can we get 32 to have a base of 4? That's my goal. Because I have 4 to the x, and I'm going to try to make this be 4 to some power. Can't do that. What if I try to make this even smaller, maybe a power of 2? This would be 2 squared x equals 2 to the 5th power. There we go. So I both have 2 as my bases. So since I have the same base, my exponents are going to be equal. That means my exponent of 2x would equal 5. X would equal 5 halves. So I'm using that rule from our previous notes. Next, we're going to find the domain of a function defined by a logarithm. A super important fact is that the argument must be positive. Okay, now the argument, if we look back at the beginning, just so that we get the correct terminology, the x value is the argument. Okay, that value must be positive. So what is input into a log needs to be positive. Okay, that's a huge fact we want to use. I'm actually going to highlight it. Argument must be positive. Because maybe you'll be solving for an argument, and if you get a negative answer, you have to say, no, not possible. So what that means is here's the argument. All I know is that this needs to be positive. So finding my domain, here's kind of a restriction I need to deal with, that it needs to be greater than 0. So as I solve, I'll get negative 12. I'm going to divide by a negative. So keep in mind, when you divide by a negative, you need to flip your sign back to the good old days. So x is really less than 3. If you want that, that's inequality. Or this would be interval notation. So that is a restriction with the domain. The argument must be positive, must be greater than 0. A little bit more about the graphs. So when you look at it, inverse of each other. Inverse of each other just means x and y's flip. If the point was xy, the inverse point is yx. Hence, it's symmetric with the line y equals x. They're inverses of each other. But really fast, don't want to skip the ln of x idea. So ln is notation for base e logarithms. So take a look. Ln of x really means log base e. So instead of writing log base e, you can instead write ln, and that is equivalent. Okay, ln of e equals 1 because ln of e stands for log base e of e. When you have equal argument and base, it's going to cancel to 1. For number 2, ln of e squared will equal 2. For the same reason, with the fact that this e will cancel with that e, and you're left with that exponent. Number 3, ln of 1 equals 0 because ln of 1 stands for log base e. Right there, equivalent. Here and here is equal, which equals 0. Since if you raise the base to the exponent, shown over here, you realize anything raised to 0 is going to equal 1. So those don't need to be memorized by any means. They're just helpful when you see ln and you're like, what? Where did log go? Well, it is a log, just base of e. We're going to end with just 2 graphs to see this inverse come into play. So first off, we're going to graph y equals 2 to the x. That is something we're familiar with from the videos before. I'm going to do a nice xy table. I'm going to plug in a negative, a couple positives, and let's see what this looks like. If I plug in -1, I would get 1/2. Anything to the 0 power is 1. 2 to the first power is 2. And 2 to the second power is 4. So I'm going to graph that. That's 1/2. That's 0. That's 2. 2 is 4. I'm already seeing that curve. We do have to keep in mind that I need you to put in the asymptotes. If you don't put in the asymptotes, your graph is not going to be accurate. Remember from our previous video, the asymptote is at y equals 0. Your graph will never cross it, no matter how far it gets in the negative. It's going to get super, 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 super close to 0, but it will not cross. And you can connect like so. Let's quickly write out the domain. The domain would be -infinity to infinity, no restrictions. The range, however, will be 0 to infinity, no negatives, and it won't actually equal 0, hence the parenthesis. Okay, well, graphing the next one, y equals log base 2 of x. Well, it's in log. I don't really know what to do. So I'm going to transform it into exponential. I'm going to take my base of 2, raise it to y, and it's going to equal my argument. This is something I can graph now. I can do a nice xy table. This time though, notice the y is the exponent. So instead of plugging in values for x, I'm going to plug in values for y, because then I can solve for x. I'm going to take 2 raised to the negative first power, would be 1/2. 2 raised to the 0 power, anything raised to the 0 power is 1. 2 raised to 1 is 2. And 2 raised to the second power is 4. So I'm going to graph that. At 1/2, it's -1, 1, 0, 2, 1, 4, 2. And I'm already starting to see a curve happening here as well. I have to be careful about asymptotes. So at the beginning, we can use a calculator to find where that asymptote would be. Or we can look at the fact that these are going to be inverses of each other. Notice inverses mean x and y flip. Look at that. So I actually didn't need to transform it. I could have just flipped those values. And that also means your domain and range will flip. So now your domain is going to be 0 to infinity. Your range this time will have no restriction. Your asymptote changes as well. Instead of being y equals 0, it's now x equals 0. And then you can connect your values. If we graphed them on one graph, you would see they're symmetric just like above. My suggestion, always XY tables. Remember, inverse just means flip X and Y. We'll do plenty of practice during class. Come with questions.